Hey, I'm Nader from NVIDIA.
I'm Carter from NVIDIA.
And we're super excited to talk to Jonathan today. John, you want to introduce yourself?
Hi, I'm Jonathan Cohen. I'm a Vice President of Applied Research at NVIDIA, and I lead the NeMo project.
Awesome. Well, we're really excited about the Llama Nemotron Ultra that just came out. Do you want to give us maybe a quick rundown on what it is?
Yeah, so Llama Nemotron Ultra is currently the best open weights reasoning model. It's trained by NVIDIA. We started with the Llama models, and we improved it in all sorts of ways, which we'll talk about today. And our goal is to make a model that's great for enterprises that can do reasoning, that can be used to as a supervisor for other models, for refining them, and can be deployed in production.
What did NVIDIA want to accomplish with releasing this model? So you mentioned it's the best open weights model that's out there right now.
Yeah, I mean, our goal is to make it easy for enterprises to build great agentic systems. Many systems that are deployed use small models, a variety of small models, but there's certain tasks that just require a smarter model that has more capabilities. And so Llama Nemotron Ultra is designed to be, the heavyweight model you can use for the really difficult tasks. You can also then use it as a basis for a distillation or what's called teacher-student training, where you start with a very big smart model and you use it to train a smaller model that's a lot cheaper. Llama is like a very popular, really you could think of it as a model platform. It's a variety of models for Meta. There's, I think, something like 100,000 variants of Llama, on the different model hosting platforms. So it's very popular. It's supported well in software. Lots of people use it as a basis for their own model training. And we decided that was a great start for us as well. So we started with the Llama models, and then we applied all of the best techniques that we know to improve them by making them smaller, by making them better at reasoning, better able to support long context, a number of different improvements.
Maybe can you explain the difference between Llama and Llama Nemotron?
Yeah, so Llama is the model trained by Meta, and they've released a number of different Llama models. The latest version is Llama 4. And Meta is committed to, they seem to be committed to continually improving and releasing really high quality open weight models. Nemotron is what we call our model training program. So NVIDIA has also released a number of Nemotron models going back several years, actually. And Nemotron is kind of a platform for us to showcase all of the best techniques we have for training models and making them good pre-training, whether it's alignment, whether it's the recent work we've done in these hybrid models. And so the idea of Llama Nemotron is to combine both. So we start with a Llama model, and then we start with the best Llama model we can get, and then we apply all of the best techniques that NVIDIA we've developed for improving models. And the combination should be the best of Meta plus the best of NVIDIA, and so that's what we call Llama Nemotron.
Yeah, so you talked a bit about the best techniques, and there were some architectural changes to Llama Nemotron Ultra that provided some better efficiencies. Can you explain a little bit about the architectural changes or the breakthroughs that were introduced in this model?
Yeah, the main one is something called neural architecture search, which is basically an approach to start with a model architecture, and then using a number of automated approaches, try to come up with a different model architecture that's cheaper for inference, so smaller, more efficient in different ways, but achieves the same accuracy. And so the technology we apply is based on this notion called a puzzle piece, where essentially you can think of the way neural networks are structured is there are many repeating identical blocks, and you can essentially decompose the neural network into a number of these blocks or puzzle pieces. You can rearrange them, you can optimize them, you can compress them, and you can put them back together. And so we have a toolkit that allows us to do this in a relatively automated way. And this works quite well. We seem to be able to compress models by 20 to 30, sometimes 40%, make them much more efficient, and at the same time retain all of the intelligence or artificial intelligence of the original model. What makes that especially attractive is you can take something that doesn't fit on a single node or a single GPU and shrink it down so that it does it. And so there's a real discontinuity in performance. So Llama Nemotron, for example, versus DeepSeek, if you think about the size difference, DeepSeek doesn't fit on a 8 H100 system, whereas Llama Nemotron Ultra does. And so if you can achieve kind of similar reasoning performance as DeepSeek, but on a single node of H100s, that makes it a lot easier to deploy, a lot less expensive, at inference time. And then especially, in this era of reasoning models, what makes a model a reasoning model is that it thinks a lot at inference time. It sort of thinks out loud to itself. And so inference cost really matters, and a model that's expensive for inference is going to be very expensive for reasoning. So being able to shrink the model down and make it more efficient for inference is really desirable in a reasoning model. And that was the focus of a lot of the work in the Llama Nemotron Ultra.
Yeah, that's super interesting. What were so it sounds like you were able to get a lot of efficiencies without sacrificing the power of this model. So we're able to run this on like a single node. What were some of the like most concerning technical challenges for a model like this?
Well, I mean, one is just the scale of training. This is a big model, so training it takes a long time. Training reasoning models requires generating very long reasoning traces. That's part of there's something called reinforcement learning, which is a stage used in turning a model into something that can do reasoning. And so you actually have the model think out loud for a really long time, generate, up to, I think we went up to about 30,000 tokens, 32,000 tokens, which is quite a long generation. So that's very expensive. So you need a lot of compute to do that. Just keeping track of, we did a lot of experiments. We have a lot of techniques for improving models in different ways. Like I said, adding long context or shrinking the model's size and complexity, adding reasoning. All of these techniques interact with each other in complicated ways. So in fact, it's a real technical challenge to do them all at the same time. It's not just like additive where, well, we have technique A and B and C, let's do them all together. It's not that simple. There's pretty complicated interplay between these. So there's a lot of experimentation, a lot of work to figure out how do we take all these things and use them together and ultimately derive the best model.
Yeah, are there a couple of like optimizations that you kind of mentioned, like you can't, it's not as easy to just kind of pair one optimization with another. Is there an example of one that kind of complicates another that comes to mind?
Well, I mean, a good example, is when you compress the model, it might just have less capacity to learn things. So you might compress a model where it's, seems by some measures similar to the original, but when you try to train it with a new skill like reasoning or long context or something like that, it doesn't actually have enough capacity now to learn that new thing. I mean, there's a pretty common pattern in training neural networks. You start with a neural network, you teach it a new thing, you train it on some new data, and it forgets. It's called catastrophic forgetting. It forgets, some of the information it had previously encoded. And so I think balancing all these things can be very tricky. It requires like a lot of thought, a lot of experiments. It's very empirical. So just being very methodical and structured, and being careful as you do it.
Yeah. So, I mean, something that's particularly impressive about this is just how much the team was able to get done technically in such little time. And so I don't know if you want to comment on how you can stay focused and be able to achieve something like this in the time frame that your team did.
Yeah, I mean, it's true. Llama Nemotron came together very quickly. I can't remember exactly, but it was like no more than 1 to 2 months, something like that. It was very, very fast. I think there's a number of reasons why. So one is, there's no Llama Nemotron team. That's not the way NVIDIA works. We certainly have teams that do things. But when we want to do a new thing, that's tricky because you don't have a team. How do you have a team to do a thing you've never done before? And so part of the corporate culture is, we call them a swarm, where you identify this is something that's important. And every manager, who has people who might be able to contribute thinks about, is this new thing more important than the current thing that everyone on my team is doing? And if I can spare some people, I'll contribute them. So Llama Nemotron ended up being a very cross-discipline, cross-team effort. We had people from really across the whole company working together without any like formal organizational structure. It was really great to see, great leadership. There were a lot of sacrifices people made, a lot of very egoless decisions that brought it together, which is just awesome. I think the other thing is, we do just have a culture of trying to be as efficient as possible. I think it comes from our heritage as a chip company. when you design chips, you're always thinking about speeds and feeds and units and wasted cycles and latency and it turns out designing a chip and organizing a process within a company are kind of similar things. So I think we have a culture of just thinking about, are we being as efficient as possible in using our people? Is there someone who could be doing something useful while they're waiting around for something else? And so I think that's just a big part of the culture. The other thing I do want to call out is there were a number of groups that were using a lot of compute that sacrificed their compute to the Llama Nemotron effort. And these days the currency in any AI researcher is how many GPUs you have access to. That's no less true at NVIDIA than at any other company. And so there are a lot of researchers who very selflessly agreed to give up their compute so that we could get this Llama Nemotron models trained as quickly as we did.
Yeah, that's definitely a one-team philosophy right there. One of my favorite things about working at NVIDIA actually is the SOL culture here. SOL stands for speed of light, and that was a new thing for us to learn when we joined. But seeing if the speed of light moves at a certain speed, what's that theoretical bound? If anything is moving slower than that, then if light's moving slower than that, then you know that there's something in the way. So then you can kind of orient to getting that thing out of the way. It's a really fun way to see a company of our size operate with such speed, right? It's like everything down to the culture is like, how do we get things out of the way and like default to getting things out?
Yeah, I think it's easy to look at some process, that I think business processes or just internal processes tend to evolve very organically and often end up being, not at all optimal, right? This team, why do you do it this way? Well, we've always done it this way. We don't get started until they file the right paperwork, right? That's just kind of how things are. And it's helpful to just continually ask the question, well, what is the theoretical optimum here? Like, if we had none of the constraints and none of this history, what's the fastest this thing could actually get done? And then always compare yourself against that. And that's this notion of speed of light where the fastest anything could move is the speed of light. So rather than measuring yourself, say, well, we're going really fast today. Yeah, but how fast are you relative to how fast you could really go? If the only real thing that bounds you is physics. So if you were to look at the physics from, kind of raw first principles, what's the actual best you could do, and then measure yourself against that, it drives the culture with just a lot of continuous improvement for sure.
Yeah, absolutely. Well, so this Ultra model is the best open weights model. What are some post-training techniques that were employed to achieve this?
Well, continuous pre-training. So you basically continue to pre-training, which is where you train the model on a lot of unsupervised data. You can just keep doing that. The way that we add reasoning is with what's called supervised fine-tuning, and we can do, or abbreviated SFT. We can do SFT with reasoning on and off. So we train the model to think differently if you've told it to reason versus not. We actually used a lot of the best open models like DeepSeek R1 to generate a lot of data. We passed that generated data through a pretty complicated filtration pipeline to make sure it was high quality. We limited the generated data, we limited to the specialty of each model. So for example, DeepSeek we used a lot for math and physics, but we didn't use it for other things. So there's a lot of work that went into where can we get the best synthetically generated data. We did a lot of work curating. The way you generate data is you feed a prompt into a model and you get it to create response, and then that's what you train on. We also do a lot of work to generate the prompts in a thoughtful way, curate them, and filter them again for safety and bias. I think another thing we did that was pretty cool was the reinforcement learning. The way it works again is you poke the model, you give it a prompt, and get it to generate a response, and then you score it based on that response, and then update the weights. So there's a lot of inference happening inside reinforcement learning, and we were able to do that in what's called FP8, or the 8-bit floating point format, which made the generation a lot faster, which made model training faster, which meant we could actually iterate much more quickly. And for a model of ultra size, that was really important. We still do the famous algorithm called RLHF, reinforcement learning from human feedback. We still do a lot of that. We have great reward models that we've also released as open, and so that's part of what gives the model, the ability to follow instructions, be helpful, safety. A lot of these things come from the RLHF stage as well. So it's a combination. I mean, training models today is a very complicated pipeline with many stages.
Yeah, it's cool to see how, as you said, training a model is just we're adding new things, and when people hear about synthetic data, oftentimes I think the common notion is, oh, the new hot thing is out, which means all the previous techniques are either gone or by the wayside. But it sounds like you're explaining there's a role for synthetic data, there's a role for human feedback, there's a role for supervised fine tuning. All of it kind of comes to play into making what truly is sort of the best in class models. You need a little bit of everything, so to speak.
Yeah, exactly. I think one way to think about it is these new techniques typically add new capabilities. And so as you keep adding new capabilities, you don't want to lose all the things the model used to, the model used to be pretty good at, if you asked it to do something bad, it would say no. Well, we don't want to lose that just because we've added a new ability to reason, right? You don't want to make it easier to trick the model now or something like that. So I think that's right, and training a model these days is a complicated pipeline with many stages, and we seem to just keep adding stages more than removing them. I think that's what that's what it looks like to me at this point.
Yeah. So part of why reasoning models have become such a big deal is their role in agents, in these agentic style workflows where a computer process is basically going off and either performing actions or kind of doing stuff on its own, if you will. So how can sort of developers actually leverage something like a Llama Nemotron Ultra in their use with their agents?
Yeah, so reasoning is really important for the planning and decision-making part of agents. So what makes an agent different from just a single large language model is a large language model is something where you give it an input and it produces an output, whereas an agent typically has some kind of more hierarchy. You could think of it as it understands the question or understands the task, it thinks about a plan of action, and then it might step through that plan and execute it. And so you typically have multiple stages. Each of those stages is often implemented as a large language model, and there's some kind of skeleton around that as well. But some of those stages, if you think about them, require a lot more brain power than others. Thinking about a question and formulating a plan for how I'm going to answer that question, that actually requires quite a bit of reasoning and thought. And so I think one way to think about a model like Llama Nemotron Ultra is it's very good at things that require this kind of deeper thought and reasoning. And so I would expect as you're building an agentic system with many stages that some of them will benefit from Llama Nemotron Ultra and some of them it's overkill. But there are enterprises that are already adopting this. One example is CrowdStrike. They're using reasoning to try to reduce false alarms from cybersecurity detection to allow the users to focus on the real attacks. And you can see why that's something where you would probably need some level of reasoning to sort of think through the evidence. SAP has an agent called Joule, which is another one. It answers questions about a company's knowledge base. And again, you want it to be able to reason about the question, think through an answer. And so these are examples of deployed systems that need this kind of reasoning. So I think reasoning models are going to be very important in future agentic systems. They're just going to get more complicated. The sort of hierarchy of thought is going to get deeper and more sophisticated and require more, let's call it, artificial brain power at different stages. And so I think models like Llama Nemotron Ultra are going to be very important.
Yeah, that makes total sense. I think as you talk to the future, or as you speak to the future of how how agentic AI and autonomous systems are growing, what are some of the future developments or enhancements that you guys have planned for Llama Nemotron?
Well, like I said, the vision of Llama Nemotron is take the best of Meta that they put into Llama and take the best of NVIDIA and combine them. So, that seems like a winning formula to me. Meta's done an amazing job with Llama. They appear to be really committed to it. They just released Llama 4, and I expect they have a great roadmap of improvements that they're going to continue releasing. And we also have a deep pipeline of technology that we're developing and inventing that we want to keep applying to these models. So things around reasoning, better ways to shrink models, better ways to handle long context, better ways to, I would say in general, looking at the limitations of the current crop of LLMs and thinking about how do we push them in different ways kind of beyond those limitations. And so taking what we're learning and applying it to the future Meta's Llama models, I think is going to be a great idea, and that's something we plan to continue doing.
So for the developers who are listening right now and they want to get their hands dirty with this model, what's the best way that they can actually access and play around with Llama Nemotron Ultra? It's open weight, but it's my understanding that there's some endpoints they can play with as well.
Yeah, so if you go to build.nvidia.com, we have a catalog of a whole bunch of models. Llama Nemotron Ultra is there. There's a nice UI. It's really easy. You can chat with it. You can play with it. You can also download it. We have what's called a NIM, an NVIDIA Inference Microservice, which is basically the model and an inference engine in a box, just in a container. You can Docker pull, Docker run, and get going with it. Or we have a number of models available as NIMs as well. You can also download the weights from Hugging Face. And then we have the NeMo toolkit, which is our toolkit for training models. So a lot of the data sets that we use to train Llama Nemotron Ultra are available. A lot of the code, a lot of the recipes. So I encourage anyone who's interested to get started with the model, the NeMo toolkit. And then for enterprise deployments, we also have what's called the NeMo microservices, which is microservices for customization, fine-tuning, guardrails, model evaluation, and a number of production-grade microservices for deploying these things at scale. And all of this is supported with what's called NVIDIA AI Enterprise, which is a single license that gives you access to all of this for commercial use.
That's awesome. Yeah, I think it's actually something very cool and extremely unique about NVIDIA is, we're spending all this money generating this synthetic data, and then we also release not just the weights, but the data sets.
Yeah, I mean, I think, our position in the world is we want everyone to do more AI and make it better. So that kind of gives us a real incentive. If we figure out a way to make AI better, we don't really have much motivation to keep that secret. In fact, our motivation is to share it with everybody we can. So we tend to release data sets, whenever we're able to. We release almost all of the source code that we use to train models. We publish papers where we explain the recipes. Anything we can do to help the world recreate what we've done, we'd like to do. We're happy to help. So I think it's, one of the things that makes it fun to be at NVIDIA is you get to be in this position of doing great work for NVIDIA and then being able to really talk about it and share it with everybody else too.
Amazing. And I think it just totally makes sense as well when you talk about synthetic data. Use the best tool that you have available. And so certain models are better at different things. And we're not here to say that there's a winner take all, right? Because people have, like with students in a class, there are people that have aptitudes towards certain things. Yeah. So you may as well leverage everybody's aptitude. And it sounds like there's a role for everybody at this pizza party.
Yeah, I think that's right. And just like I don't expect, like someone will use Llama Nemotron models and nothing else. There's a lot of great models out there, and many of them are really good in different areas. We are trying to fill niches that we think are maybe a little bit less served with the models that we create. But in general, yeah, I think that's exactly right. We use other models as training data for our models. We expect our models will be used to generate great training data for other people's models too. And it's I think part of why the ecosystem and the community is moving so fast and innovating so fast is because, in fact, there's so much collaboration across different companies and academic groups and people. Yeah, absolutely.
Yeah. Well, amazing. We'll put a link to the link on build.nvidia.com so that it's really clear for everyone to get started. Build also has unlimited credits for developers who are playing around with this endpoints. So yeah.
John, thanks so much for coming on.
Awesome. Thanks, guys. Great to talk to you.